Okay, welcome back. Today's class, Tuesday, April 10th. So we'll continue our discussion on deep learning. Specifically, we would like to look at some applications of deep learning. So first, what I will do is I will, in fair amount of detail, describe an architecture called LXNet, which was one of the first very successful attempts applying convolutional neural networks to large-scale problems of classifying objects in images, right? So given an image, we would like to identify what object appears in that uh, image, right? And this paper appeared in a conference called NeurIPS in 2012. So we'll look at the architecture and also look at some of the results of the paper. Then I will talk about a blog which describes some very cool applications of deep learning. Ideally, in a regular classroom setting, I would have gone through those applications in an online manner, but I think for a video lecture, it makes more sense for me to sort of point you to that blog. You can look at it as you go through this lecture when you come to that slide, and then continue reading this lecture, right? And of course, any questions, any discussions can happen over Piazza or in the QA session. Later part of this class, I want to start sort of the last subtopic of this course, which is unsupervised learning. That is where we don't have labeled examples, but we have only sort of the features for each of the examples. No class label is given, and the question is, can we do something interesting in such scenarios, which is the topic of unsupervised learning. Okay, so this is ImageNet classification with deep convolutional neural networks by Alex Krzyzewski et al. This is from Jeff Hinton's group at University of Toronto. Jeff Hinton has been one of the leading sort of experts in the arena of deep learning. In fact, it would not be an overstatement, right, if one would sort of consider him as one of the fathers of modern day deep learning. Uh, right, and as I said earlier, this particular paper describes the first large-scale application, successful application of convolutional neural networks to a real life problem, which is classifying objects in images. They developed a system called LXNet, right? And this particular system was demonstrated on a subset of ImageNet. So ImageNet is a large data set of images with objects in them. I think they have several million images. So as part of advancing the research in the community, what has been done, and which is pretty common these days, is that you sort of create annotated data sets which become standard benchmarks for people to test out their models. And ImageNet, this subset of ImageNet was created, I think, in late 2000s, which is 2007 or 8, if I'm not wrong, to really push forth the research in computer vision, right? So this appears as part of this is called ImageNet Large Scale Visual Recognition Challenge, right? And this LXNet architecture was applied on this ILS VRC dataset, which has about 1 million images. To be precise, I think it's 1.2 million images for training, 50,000 for validation, and 150K for testing, right? And each image can have, I think there maybe multiple versions, but the version that we will talk about in this paper is that each image has exactly one object, and this object could come from one of the thousand object categories, right? So it's sort of a 1,000-way classification problem, and the way you evaluate this particular the evaluation metric could be there are two ways that people typically evaluate. One is top-down accuracy, right? So typically what will happen is that your model will give a probability for each object class, right? So it will say that maybe a particular object appears with a certain probability, some other object appears with certain other probability, and the total probability adds up to 1. right? So top one accuracy means that if I just take the top scoring object based on your model, right, how many of them are correct, right? And top five accuracy is somewhat lenient, so it is saying that if your correct label appears in the top five predictions of your model, then you say the model is accurate, right? So people evaluate on both of these accuracy numbers, and we will see results of this particular architecture vis-a-vis the state of the art at that point of time. Okay, so let me describe this slide which presents the architecture of AlexNet, and this image has been taken from the paper itself as is written here. The image and caption source is the paper by Alex Chris Spy. Right, and this particular architecture has eight layers, I believe. Um, right, and I guess there are seven hidden layers, and one is the final sort of output layer. Right, and let me describe this architecture in detail. Right, so the way to read this would be right. So let us look at sort of the first layer, which is the image itself, right? So the image, if you read the numbers 224, 224, 3, right? So these are images, right, which are given to the system, which are 224 by 224 height by width, and 3 is essentially 3 channels, which is RGB, right? So this is the image that is given to the system, right? And these dotted lines, right, denote sort of this image being fed into the operation leading to the next representation or feature map, right? And if you look at this 11 by 11 box, right, this is a kernel, right? So what you're doing is that you're applying this 11 by 11 kernel, right, convolving the entire sort of image, right, with this kernel, to get the next feature map, uh, right? And uh, and uh, right, so there is a stride of 4 in the beginning, right? So which means that right, so image size would be sort of reduced by 4 in each dimension, right? And that is demonstrated in the next feature map, the second part, right, of this layered architecture, right? So 224 goes to 55. I mean, there is some truncation here, so it's not exactly by 4, but 224 by 4 is about 55, right? And what is this 48? Right, this 48 is essentially uh, the depth in this in the second feature map, right? In the side after the first application of the first convolution, right? So it is this depth. Remember, the depth here comes from the fact how many kernels are being applied, right? So here, in some sense, 48 kernels are being applied. Right, so what happens here is that there is a bit of detail that it's not 48, but in fact 96 kernels are being applied. And the way it is being done is that right, this is not something which probably occurs today, but back in 2012, these feature maps take and these operations take a lot of memory, and they have split this operation across two different GPUs, graphic processing units, and 48 of these kernels are being operated on the lower or the first GPU, and 48 are being operated on the upper one, right? Therefore, sort of split your feature map across depth, 48 being in the lower one and 48 being in the upper one. So there are actually 96 such kernels being applied in the first operation, right? And then you get this 55 by 55 by 48, and similar sort of replicated on the other GPU, right? And then what happens is that they apply max pooling over this, which again reduces the size that we can see in the next layer, right? So you apply max pooling, and after that you apply a kernel which is 5 by 5 cross 48, right? Because um, right, so here the depth is 48, so you apply this kernel, which is 5 by 5 cross 48, and note that in this sort of second layer, the two feature maps on two GPUs are being processed independently, right? So each one has its own sort of kernel operations defined by this 5 by 5 cross 48 sized kernels, right? And this operation leads to the next layer, right? And there are 256 such kernels which are being applied, right? So again, right, it shows up in the next feature map, which is the third um, sort of column here of images, right? So you have now 27 by 27, size is reduced to half because of max pooling. I guess pride here is 1, and 128 of these kernels in the depth show on the lower GPU and 128 on the upper GPU. Note that the representation for the upper GPU is not complete in the image, just to make it clear, right? And in the third sort of layer, right, what they have done is now they have um, done again before the third layer, right after the second layer, max pooling is applied, and in the third layer, they have applied 192 plus 192, which is I guess 384 kernels, and each of size 3 by 3, uh, and of depth 54, which is 27 plus 27. And why 54? Because in this case they are allowing interaction of feature maps from two different GPUs, right? So each kernel that is being applied is being applied to the lower sort of image, lower feature map, and also the top feature map. uh, right, and therefore you get the next layer or the fourth layer, and so on and so forth, right? And after that you see there is this is the third sort of application, so you get the fourth feature map, which is this 192 um, by 13 by 13 sort of feature map, each on each of the two GPUs, and then you apply the fourth convolution, right? Stride is 1, there is no max pooling, so the size does not reduce. This is independently applied on each GPU, and then you apply uh, one more operation, the final convolution operation, which gives you this box of size 13 by 13 and 128 depth, right? And I have not explicitly mentioned the number of kernel applications, but in the fourth layer, but you can right figure that out, that it is again 384. In the fifth application, there are 256 kernels which are being applied um, to get this final feature map, which is where there is written max pooling in the fifth feature map. Okay, and then finally, what happens here, which I think is important, right, which is actually quite important to understand, is that once you sort of convolve, which is a local operation, right? So by this time, sufficiently sophisticated feature maps have been computed by this fifth layer, um, and in fact people have um, done some experiments to sort of visualize these features at different layers. Maybe I'll point you to some references, but once this is done, it is quite typical to have a couple of fully connected layers, just to allow flow of information from one part of the image all across to the different parts of the image, right? Convolution operation being local, right, until this layer, right? Most of the sort of operation is being applied locally, especially locally, but these final sort of fully connected layers help you circulate information all across images, right? So these are also called dense layers, right? These are applied, so there are three dense layers, two of size 4096, followed by a dense layer of size uh, 1000, right, which gives you the final sort of feature map, or the final object probability, right? So this is the entire architecture, which gives you the final probabilities of each of the classes, right? And there are some details here in the caption that you can read, but I just wanted to go through this to describe how to read this sort of CNN architecture. So this slide is interesting because this, right, so the image here is again taken from the paper by Chris Vespe et al. 2012 paper. Right, so this particular image on the right describes 96 kernels which are being learned in the first uh, after the first application of convolutions. um, right, right, you may say, what does it mean to represent kernel in this image form? Right? And let me sort of draw a picture to illustrate what's happening. Right, so this is sort of your image, right, initial image on which the kernel is being applied. So this is 224 by 224 and depth is 3. Right, and remember initially they were applying kernels of size 11 by 11, and of course the depth is 3, right, and then there are I think 96 such kernels. Right, so if you remember the operation, the convolution operation, we had x, right, I plus u, and then j plus v, and I believe we used the letter L here, uh, dot w, u, v, and L, right? Sum over possible values of u, v, right? To really get your right next feature map, right? And of course there was a plus b, that is the bias term, right? And if you look at this operation, these w's are again sort of real numbers which are being learned, uh, as the training proceeds, right? And because they are being convolved with the image, right? So you can think of these w's also as right, when appropriately normalized to 0 to 255, or 0 to 1, depending on how you present an image, right? This could be thought of as actually representing some kind of feature map or an image, right? I hope that makes sense, right? Because and it is often a practice to consider these kernels, right, or these weights as sort of representing underlying images, right? And the whole idea is that because it's a dot product, right, and in some sense, what will happen is that when the neuron is being fired, it will right, the output neuron will be high when x has a high dot product with w, right? Which means that whenever x is similar to w, right, those features will be selected, right, in the next layer, right? So this w is a good representation of what is being detected in the image, right? Because when you take the dot product, if the pattern is similar to what w is representing, then it will pass on. Otherwise, you will get sort of a lower probability for that particular pattern, right? So in sort of nutshell, or in summary, right, these right, 96 are essentially the patterns, right, which are being learned in the form of these kernels, right, which are being applied or convolved with the input image, right? And you can think of this is exactly the pattern, or right, which is being recognized by the corresponding filter, right? And you could do sort of a similar exercise later. Maybe one has to think more uh, about what these representations might be, but right, I guess there will be some kind of higher level feature representations. um, but in the initial layer, right, these are detecting, if you will, things like edges in the image, right? Different kinds of edges in the image, and these are passed on to the next sort of layer for complicated more complicated or more sophisticated representations. And for more details, I'll refer to the paper, and of course, I'll be happy to discuss in the QA session that we have planned tentatively, I guess, on Sunday. I'll again sort of announce on Piazza, and of course, feel free to post things on Piazza as well if you have any questions. Okay. So on this slide, right, we look at the actual results of the model proposed by Krichkowsky et al. In 2012, and these images have been taken from the paper as is described in the image source. Right, so let us look at the set of images on the left, right, which is right next to the visual results column. Right, so there are 12 images, and each image shows you a test image, right, which is given to the model, and right below the image the actual ground truth, right, or the correct label is described. Right, for example, the top left images of a mite, right, and similarly, each of these 12 images have the corresponding ground truth label. So there is a mite, there is a container ship, there is a motor scooter, there is a leopard, grill, mushroom, cherry, Madagascar cat, right, and right below the ground truth for each image, five, right below the ground truth, right, what is shown is the top five object categories which are output by the model, right. So for each output category, the model will assign a probability, right. So you take those five object categories which get the highest probability and display them in the order of from highest probability to the lower probabilities, right, and the red bars essentially show the object categories which were actually the correct class labels, right. So for the top four images, you see that the model was actually able to get the highest probability to the correct answer, right, which is good. Right, and in the lower four images, right, the first two, the object was not able to get the correct answer at the top, but it was the second one, which is still okay for top five accuracy, and the last two, the model made incorrect predictions even on in top five, right. So the correct answer did not appear in the top five, right. So this is just demonstrating the kind of output that you get from the model. On the right side, this set of images is I think more interesting, right? So on the right side, the first column in each row is actually a test image, right? So this is the image for which the model is asked to make a prediction, and right next to it, in each row, there are six images which are being displayed, right? And these images are from the training set, and these six images are those images in the training set which have the highest similarity to the test image in terms of the feature map at the final layer right before the output is produced, right. So what you do is, right, that as you pass the test image through the model, right, you get a feature map right before the output layer for the test image, right, and then you do the same thing, right, for each of the training images, or rather you would have stored these feature maps for each of the training images, uh, right, once the model was trained, right. Right, so once the model is trained, right, for each of the training images, you also store these feature maps corresponding to the trained model for each of the training images, and then for each of the test images, each of the test image, you display those six training images which have highest similarity in terms of the final feature map, right. This hopefully makes sense, right? Because what it is saying is, the if you look at the similarity of train and test images based on the final feature map, right? Then what the model is computing is something meaningful, right? Because what is similar in terms of the final feature map in the training and the test images, right, also corresponds to a notion of visual similarity, right? So which is very nice. Right, because as I said, right, the feature maps are actually corresponding to what we would perceive as similar visually, right? Okay, and on the left side, right, leftmost column shows visual results, right. It describes the visual results of the model over then state of the art baselines, right. So these are very hard tasks, right, and at least this is 8 years back, and right, maybe I guess the state of the art has improved quite a bit, but at that point of time, this LXNet model was able to get an error rate of 37.5%, which is, I guess, 62.5% accuracy for the top one metric, and 17% error rate or 83% accuracy for top five error rate, right? Of course, the error rate is lower for top five prediction because it is an easier task. And what I think is more important to note is that there was, up to 8% improvement over the then existing baselines, right? Right, and this 8% is really significant, when one realizes the fact that, even to get 1 or 2 point improvement in scores over some of these data sets can be quite challenging, right? So much so that, right, this was such a sort of huge improvement that, right, that CNNs really became popular after this paper was published. And for, many of the future applications, they, right, for image analysis, they became sort of de facto standard, right, and a lot of research sort of built on this initial idea of CNNs, leading to much advancement in the field. Right. So I just want to make one remark before we proceed. From my previous description, you should not get the impression that these architectures are sort of among the first ones to propose things like CNNs, right? In fact, CNNs and RNNs have been around for more than 2 decades, right? The theory was proposed much earlier, but what has happened in last few years, last decade or so, right, that people have been able to really apply them to large scale problems because of, availability of compute power, large scale data sets, and also advancement in, specific architectures as well as, training methods, right? And all these things coming together have, really brought them to the fore of research, where, not only in terms of research, but even in terms of um, real world applications, they have become really prominent across the academia as well as industry, right? Okay, and having said that, I want to, point you to this blog by someone called Jason Brownlee, and I find his blog to be quite useful and interesting for machine learning related topics. Specifically, I came across this when I was teaching my class on deep learning. Right, this is about various cool applications of deep learning. I think he describes 10 of them. And this is from somewhere in 2016. He might have updated the page a bit. So some of the applications might be a little bit older, but I think they are still quite illustrative of what, kind of things deep learning can achieve. And he describes applications all ranging from, automatically coloring black and white images, to colored images which make visual sense, to automated text generation. For example, what if you were given text of right, written by Shakespeare, and could you train a system which could write in a similar style? And there are many such very interesting examples from image as well as language domain. So I will encourage you to spend about 10-15 minutes on reading those applications, maybe looking at the videos, and then you can continue back with it. Okay, great. Right, so this really completes whatever I wanted to cover on deep learning, and in fact, this also sort of completes whatever I wanted to cover as far as supervised learning techniques are concerned. Right, we will have a set of lectures on learning theory, which talks about generalizability, um, and principles behind, how could you make correct predictions on future instances. That will be sort of the last week. But before that, let me spend a good amount of time that we'll spend now is on unsupervised learning. And these are the techniques, different from supervised learning, because in this case, you are not given a label data, right? So for example, recall that supervised learning setting started with this set of features, right, for each example, right, which were represented by xi's, and these yi's were the class labels, right? And then the goal was to sort of learn a hypothesis, right, parameterized by some h theta, right, which would take your x and produce a y, and right, y hat. And for given xi, right, we wanted this y hat I to be as similar to yi, right? And this was called supervised learning, because of the fact that supervised learning, right, because of the fact that supervision was given in form of these YIs, right? So now the question arises, right, and in fact, we, right, just to sort of summarize very quickly, we looked at a lot of algorithms, right, around the supervised learning. We looked at linear regression, we looked at logistic regression, right, we looked at GDA, Gaussian discriminant analysis. We looked at SVMs, that is support vector machines. Um, right, we looked at decision trees, and in that context, we also looked at random forests, and then we also looked at uh, finally, right, the last topic that we covered, that we sort of completed just now, was neural networks and deep learning. Right, so we looked at fair number of algorithms, right? This was actually a regression algorithm, right, where your yi's came from the real valued space, and all others were sort of the classification, right? So where the y belong to a discrete set. Okay, so now, right, moving on, the question is, right, suppose now that this yi is not available to you, right? And what is given to you essentially is a bunch of examples, with where each examples comes with a set of features, right? And this is essentially the realm of unsupervised learning, and the question is, can you do something interesting here? Right, so even when yis are not given to you, right, so can you do something interesting, is essentially the question that unsupervised learning tries to answer. And we will see that in fact the answer is a big yes, right? So even if yis are not available to you, you can do some very interesting um, analysis and very interesting things with the data that is given to you, even in the absence of supervised labels. So let's look at some of these techniques in the next slide. Okay, so let me, before we proceed to specific techniques, let me draw an example which should remind you of our earlier example with monkeys and chimpanzees, right? So let's say we go to a zoo to watch some animals, and we observe, the two attributes of each of the animals, which is the height and the weight, right? And in the supervised setting, we were given these examples, right, where for each animal we were given the height and weight, and we are also told, whether it is a monkey or chimpanzee. Now in the unsupervised case, you think of the same example where someone has collected this data, but now uh, they have not provided you with yis, right? So you don't know whether the animal is monkey or chimpanzee, and for now you can assume that you are still dealing with two animals, right? So you can give them the labels monkeys or chimpanzees, monkeys and chimpanzees, or it doesn't matter, right? So someone tells you that there are two kinds of animals in the zoo, and I'm only going to give you the height and weight of the each animal, right? And I'm not going to tell you, which point was generated from with set. Right, now the question is, can you still do something interesting, right? And right, let us look at this particular picture, right? And this is, let's say, how the height and weight of these animals are distributed, right? So in this case, it is not very difficult to see that you can in fact do something very interesting with this data, right, even in the absence of any yis, because visually, right, there are two clusters, right, that we see emerging from this data. And then these clusters could be given some labels, let's say L1 and L2, right? Right. These are sort of your hidden or missing labels, if you will, right, which are assigned to these clusters, right? And if you knew that the specific classes that this data comes from, then this could be, your specific monkeys and chimpanzees, for example. Uh, okay, so right. So given this setting, right, so I will sort of separate out, you know, unsupervised learning in three broad sort of categories that we'll talk about. The first one will be clustering, right? And this in particular will concern with simply clustering the set of points which are given to you in a given set of clusters, and then for most part, for our sort of uh, our exposition will assume that there is a fixed number of clusters that is known to us, right? So we know, how many clusters are given to us in the data, how many clusters are there in the data, and then we have to discover those clusters. That is, we have to assign each data point to a particular cluster. The second set of things, the second set of techniques that will develop around this would be called density estimation, right? And here the goal would be to essentially, um, given a data point x or xi, right, you would try to um, assign it a probability based on some parametric model, underlying parametric model, which is parameterized data, right? And the way we would do this is we would sort of assume that, there are some hidden labels zi's, right, for each of these xi's, right, which are missing, and we will try to predict those, right, um, and and then use those in turn to uh, to build our model of density estimation, right? And in this context, we will look at two techniques called GMMs, or Gaussian mixture models, right, which are uh, sort of a generalization or extension of um, GDA to the case when there is missing labels. And we will also look at a very important classical algorithm called expectation maximization, right, which is a general technique to deal with missing data. And in this case, for example, the missing data is ZIs, right, which can also be thought of in the as cluster labels, right? And something I forgot to mention is that in case of clustering, we will use, or we will study the popular k-means clustering algorithm, right, which works with this k set of means or centroids and assigns each point to each cluster, right? And in fact, we will start with k-means and slowly sort of build on the theory to go to density estimation, and we'll see that the kind of techniques that we'll study for density estimation can also be used essentially for clustering. And then finally, right, we will study what is referred to as PCA, or principal component analysis, right? And this is a technique for dimensionality reduction, right? And here the idea is that given a data in a very high dimensional space, right, you figure out underlying pattern in the data, uh, right? And for many problems, you can show that the data lies in a much smaller subspace. And if you can identify that subspace using a set of mathematical techniques, then your learning becomes much more efficient, and you can also deal with overfitting efficiently. And this is again done in the context of unsupervised setting, where your labels are not given to you, right? So these are sort of the broad set of techniques that we'll study. And maybe, right, rather than going into each one of in gory detail in this class, let me sort of give you a broad idea of each of these techniques in this class, and then we'll build on that in the following. Let us come to clustering first. right? So what is clustering? So the clustering problem says that you are given a bunch of data points, xi equal to 1 to n, and each xi could belong to Rn, and we'll assume that they belong to some real dimensional feature space. Okay, and then the goal or the objective uh, is to assign uh, a variable ci, right, which is sort of the cluster identity of each of these data points, right, where each ci belongs to a set of uh, clusters given to you, right? So there is these indices refer to the clusters that lie in your data, and each ci belongs to one of these k clusters, right? And for each point xi, you want to determine this cluster identity ci, right? And there are some questions that you really need to answer to be able to do this well, and you'll see some parallel with supervised learning. That the first question that you need to be able to answer is that what are the properties of a good clustering? Right. So how do you sort of mathematically define, right, what is a good clustering, right? So in the previous slide we saw that the a good cluster, at least visually, would be where points which are close to each other are assigned to the same cluster, right? So what is sort of the mathematical equivalent notion of which sort of formalizes this notion that points which are in the same cluster should should be close to each other, and points which are probably far away should belong to different clusters, right? And then given this, given this sort of mathematical definition of what is a good clustering, right? So how do you really find uh, this this clustering, uh, right, automatically, right? So in some sense, how do you discover this clustering, right? So describe an algorithm, right, to discover this clustering, right? And this will be essentially, right, our k-means algorithm. And actually, let me just correct, this should be m, right? And note that combinatorially it is not an easy problem, right? Because if you were to randomly sort of assign a cluster id to each of the points, then there are k to the m such possible clusterings which are possible, right? So you have to be sort of efficient to discover this notion of uh, good clustering and actually figure out this assignment for each of the data. Okay, the next set of topics that we'll study will be around the problem of density estimation. Right, and as I said earlier, this idea of density estimation will sort of subsume the clustering problem, because once we would have estimated the density, right, we would also be able to sort of figure out the clustering as a fallout of this process of density estimation, right? And what is the density estimation problem, right? So let me draw the diagram again that I had drawn earlier, right? So you are given this data with two features, x1 and x2, right? And for any given data point, right, you want to figure out, right, what is the probability of xi, under some parameterized model with parameters theta, right? And here we would sort of take inspiration from our sort of GDA model, or Gaussian discriminant analysis model. And remember, there we had sort of two quantities, right? So we had these class labels, right, called yi's. Here we will refer to them as zi's, right? And zi's will belong to a underlying classes which will be unknown to us, right? But we'll try to estimate them. And given these sort of zi's coming from certain distribution, right, we'll now try to estimate probability of xi given zi's, given by theta, right? So what essentially we are saying is that, right, this pxi parameterized by theta, this density estimation problem is translated into a slightly different problem, which is understanding or trying to estimate the parameters of this pxi, zi, theta, where zi's are unknown, right? So what we are saying is that the underlying model is actually describing a joint distribution over these xi's and zi's, but zi's are missing. Therefore, we have to sort of marginalize over these zi's to get the probability of xi parameterized by theta, and this will be coming from some parametric form, right? For example, this could be expressed in the case of GMMs as probability of xi given zi theta and into probability of zi parameterized by theta, right? And of course we would sum over all zi's, right? And and pictorially, right, this essentially corresponds to learning these Gaussian distributions, right, around the corresponding centroids. But note that we in this case we really don't know uh, right which point came from which Gaussian distribution. So not only we have to estimate the parameters of these uh, of these Gaussians, but we also have to estimate the class labels, or what we the assignment of each of the points to the to one of the clusters, right, or one of these Gaussians, right, which we refer to as i's, right? And think of the i's as replacing yi's, right, in the supervised setting. Um, and this will lead to an algorithm, or a model called Gaussian mixture model, right? Let me write it here: Gaussian mixture model, right, which essentially will describe each point as coming from a mixture of Gaussians, right? So each point will get a probability of being picked from either of the clusters, and it will be sort of between 0 and 1, and once it is picked from a particular cluster, right, we will say what is the probability of generating that particular point, the set of features given the cluster identity, right? And then we will study the algorithm called expectation maximization, which will sort of generalize this idea of uh, estimating the cluster identity zi, and then correspondingly um, finding the parameters of each cluster, right? So this will be around density estimation and expectation maximization. And finally, we will study what is referred to as principal component analysis, right, or PCA, right? This will be actually linear, in the case of sort of this will be linear PCA, right? And this is a technique for dimensionality reduction, right? And let me sort of describe the basic idea with the help of a picture, right? So suppose you are given some data which is let's say lying along two dimensions, x1 and x2, and this is probably different from your monkeys and chimpanzees data, and let's say these are your data points, right? And right, and this is given by the set of, right? And as you can see that although this data is being described by these dimensions x1 and x2, but what is happening here is essentially this data probably lies along this single dimension u, which is sort of a linear combination of this x1 and x2. That's why it's sort of linear PCA. And right, we would really like to understand first that if there is a sort of a smaller subspace, right, of the original space where this data could be projected. This is a simple example with just two dimensions and projecting into one dimension, but in general, your xi could belong to some large n-dimensional space, and you would like to project each xi onto some u1 to u capital K, um, right, smaller vectors which span a smaller subspace, uh, right? right? So you want to project this n-dimensional space to a much smaller k-dimensional subspace, so that right, most of the variance in the data is captured, right? For example, in this case, if you project these black dots onto this line, right? And note that this is a sort of a uh, nearest projection of each point onto the line, right? So if you really project each of these points onto this line, and then most of the variance in data is still sort of captured, right? So, and in general, we are looking for this u1 to uk, which in the original space, right, each of these ul still belongs to Rn, right? But we could essentially take k of these vectors in the original Rn space, and and construct a subspace which is essentially k-dimensional, and project each of these vectors um, to each of the original vectors to this smaller subspace. And we will see that this has several advantages. And one is that it reduces dimensionality without really losing much information, right? Which can greatly help reduce overfitting, and also make training much easier. And as I said, this also helps reduce overfitting and or dealing with noise in the data, because when such a projection happens, hopefully whatever information is lost is was essentially due to noise, and therefore is gotten rid of as the data is projected to a much lower dimensional subspace. We will talk about something called eigenfaces, right? Where we will see that for the problem of recognizing faces, for example, in images, right, you could project thousands of dimensional space to a much lower 50 or 60 dimensional subspace, and still preserve most of the information. Right, right, and just to sort of connect back to the example in the image, right? In this case also, if you project the red points to the closest point on the blue line, then hopefully, right, as we can see, much of the information is preserved, and these these sort of black points can now be represented as in terms of a single scalar, uh, which is just a coefficient of this u, right? So that is what I mean by projecting this data onto lower dimensional subspace. Okay, I think I should stop here, and then we'll continue these topics one by one in the next class.